continuing Ndefo Okigbo classes. We are continuing with, this is lecture 7, dealing with beams. We have dealt with simply supported beams. We've dealt with frames. We are going to deal with continuous beams. Normally continuous beams are indeterminate, but like these ones, they are determinate just because of the application of a hinge. If you look at point D, look at the beam. The beam is A, B, C, beam A, B, C. That's the beam we're going to solve now. But at the point D, there is a hinge. A hinge is a point of flexibility in a beam. Because the beam, throughout the beam is rigid, the beam is stiff. But at a point where we introduce a hinge, that point becomes flexible. What do we mean by flexibility? At the point of flexibility, it's no longer rigid as other points. It's no longer stiff. That means it cannot resist bending moment. It will bend if bent. Other areas will resist. That means a stress factor has been removed from that point. That's a bending moment. That's what made the beam would have been indeterminate. But for the fact that a factor has been removed, that would have made it indeterminate by the introduction of the hinge. That factor is bending moment, because the hinge introduced flexibility at that point. So that point D. So with that now, we can still solve this beam like a determinate beam instead of indeterminate. Looking at it without the hinge is indeterminate. It's indeterminate without the hinge to 1 degree of indeterminacy. But with the introduction of the hinge, it now became determinate. So since it is now determinate, to solve it, what we do is to cut it at the hinge, because if you cut it at the hinge, there's no bending moment. If not any other place you cut it, there will be an internal bending moment, which you need to analyze and get its value. But for the fact that there is no bending moment at the hinge because of flexibility, you can cut it there. So that's why we now cut the beam and get this beam AD, this small beam AD with the same load. What we now do is that we solve the beam AD first. After solving the beam AD first, the reaction at D will be loaded on the beam at point D. If you load it, look at this. That is AD broken. The reaction at D is rested on the beam at point D. Look, that is this. If you look at this beam, so when we now do that, when we analyze this beam, we get that reaction. We got it. You will see how I got it 4.8. So I brought it onto the next beam, that is beam BC at point D. We brought it. So now let's deal with the first branch of the whole beam, which is AD, as we call it at D. So to get the reaction at D and work that AD part of the beam so that we load it on the next one. That is how we deal with beams that are continuous, that are also made determinate by the introduction of hinge. Ordinarily, we cannot solve an indeterminate beam this way. There's a procedure when we get to indeterminacy. But for the fact that a hinge is introduced here, this beam becomes determinate. Now, I can break it at that D to get a soluble beam, which is AD. So if I want to deal with D now, I get the reactions. I start. I say I want to get reaction A, so I take moment about point D. Total moment about is equal to 0. That means I have 5, because the distance from D, from A to D is 5, 3.3 plus 2. So 5 RA this way, minus 8. 8 is the load times 2. That's the distance from the load to D. So there's no other load. The reaction D will not generate moment at this point because of 0 distance. So that means this is equal to 0. Total distance, total moment at point D is equal to 0. If that's the case, that means RA is equal to, from this equation, 8 times 2 is 16. RA is equal to 16 over 5. RA is equal to 16 over 5, which is, RA is equal to 16 over 5, which in this case, 16 over 5 is 3.2. 16 over 5 is equal to 3. That's 3.2. ROA is equal to 3.2 kilonewton. That is the load. The reaction at ROA, then let me get the reaction at ROB. So at ROD, total moment about A is equal to 0. So I start 5 ROD, 5 ROD, and minus, because I return this way, the load turns against it at A, minus 8 times 3 this time, not 8 times 2 again, because the distance of the load from A is 3, equal to 0. ROD is equal to 8 times 3. Is equal to 8 times 3, which in the 8 times 3 is 24. 8 times 3, 24 over 5, which is equal to 4.8. Equal to 4.8 kilonewton. That's how I got this 4.8 ROD that I'm landing on the next beam. The 4.8 I put on the next beam. This is how I got it. So as I got that, the next thing I've gotten the two reactions. I can now get bending moment. I can get bending moment on that small beam AD. I can get bending since I've gotten the reaction. If I want to get bending moment at A at point here, let me call this point E. Let me call it point E at 8. So simple. I have M at E. M at E is equal to, the only thing there is reaction A, which is reaction 3.2. 3.2 times the distance, which is 3. 3.2 times 3, because that's the only at that point, which is 9.6 kilonewton meter. That is the moment. So with this, I come to the next beam, the beam BC. I've dealt with AD. I'm working the whole beam. So I'm now at beam BC. So at beam BC now, I have found a reaction, which is 4.8, which I got from here, reaction at D. I load it on beam BC, on the cantilevering part of BC, that's at point D. I load it. That's how to solve beams that are continuous but determinate, because there is hinge in the beam. So to deal with BC now, I want to get reaction.